Okay, so in this video, we're going to discuss fundamental trigonometric identities. And that's what we'll see here in this table 6.1, actually from the textbook. So the fundamental trig identities consist of the reciprocal identities, which we've already discussed, right? So we can write, sine x is the same as 1 over cosecant x. Cosecant x is the same as 1 over sine x. Likewise, when we originally defined secant x, we think of that as 1 over cosine. Well, we can also think of cosine x as 1 over secant x. And then the same is true with cotangent and tangent. We can also express tangent and cotangent with what we consider to be the quotient identities. The tangent is equal to sine over cosine, and cotangent cosine over sine. So we've discussed those, but now we want to formally refer to them as the reciprocal identities and the quotient identities. So now we're going to bring in the Pythagorean identities. So this comes from Pythagorean theorem, as you might suspect. And so I would like to just show you where one form of this comes from. So if we think about this first one, sine squared x plus cosine squared x equals 1. Well, let's consider a right triangle. We'll pretend that's right? That'll be my right angle. And I'm just going to call this leg A, this one B, and the hypotenuse C. So from that, let's look at this angle as theta, right? So I could say, okay, sine theta opposite over hypotenuse, so that would be B over C. Cosine theta adjacent over hypotenuse, so that would be A over C. And then we would, of course, think tangent would be B over A. But now let's go ahead and I'm going to divide each side by C. Okay, so C over C, right, we know that's 1, that's number over itself. A over C is cosine, right? So this is the same as cosine theta. And B over C, that's the same as sine theta. So the Pythagorean theorem says that one leg squared plus the other leg squared equals the hypotenuse squared. So that would mean that sine squared theta plus cosine squared theta is equal to 1. And so that's where that identity comes from. We could do similar things to consider the other two. But I just wanted you to know that that is related to the Pythagorean theorem that you already know and how those are derived. Another thing I think that is good to point out is that when we're squaring a trig function like cosine squared, we write it as cosine squared theta. So that notation you'll see that you may or may not be familiar with. And so the last are the even and odd identities, which is sometimes discussed in algebra. And this really has to do with symmetry. Even symmetry is symmetry with respect to the y-axis. And odd symmetry is symmetry with respect to the origin, meaning the 0, 0 point on the xy plane. And so if you think about this kind of symmetry and you consider these graphs really quick. So let's first think about y equals sine x. So if I'm going to consider just one period, right? This is 1, this is -1. So we know it goes like this, right? And it would go like this on the other side. So if I'm just considering one cycle, I want to kind of keep that origin in mind. We could see, although my graph isn't drawn beautifully, but this would be considered to have origin symmetry, right? So if this is pi over 2, and we know that point pi over 2, 1 is on the graph, negative pi over 2, -1 is also on the graph. And so that's where this identity comes from. So for example, if I think of sine of positive pi over 2, that is equal to 1. But sine of negative pi over 2 is equal to negative 1. And so you could say that that's the same as saying negative sine of pi over 2, again, would then be equal to negative 1. So likewise, cosine actually has y-axis symmetry, and so it's going to behave this way. So if you think about what the graph of cosine looks like, cosine at 0 goes up to 1, right? So if I'm looking at a cosine graph, and I'm really considering just what is around the origin there, that's that, again, that's that y-axis symmetry. And so if the input is negative, so like if I put in, let's say, that would be negative pi over 2, and then this is positive pi over 2, the outputs are exactly the same, right? Cosine of pi over 2 is equal to 0, and cosine of negative pi over 2 is also equal to 0. And so the other trig functions behave similarly, and those are considered to be the even and odd identities, again, based on symmetry. So what we're going to do in this section is we're going to simplify trig expressions in a couple of different ways. So that's one example that we're going to look at. Then we're going to look at another example doing the same thing. And then we're going to take a look at a couple of questions from the homework. So I want to show you also how to input some of these things. So you'll also be looking at some where we're going to prove the identity, and we'll actually be selecting some of these specific identities to justify the actions that we're making. So let's take a look at a couple of examples, and then we'll just kind of go from there. So the first one, so number 1, we're going to simplify the expression tangent x cotangent x. And notice the directions say use algebra and the fundamental trigonometric identities, and our answer should just be a single trigonometric function. So I'm taking the two functions being multiplied together, and my final answer will just be a single function. These are some guidelines, some suggestions that we could use to help us get there. So with these, we're going to always just work with one expression. If this had been one that we were proving, it would have it equal to something else. So we would want to show that one side is equal to the other. So that's why it says let's just work on one side of the equation. Look for opportunities to apply the identities. So kind of things that you want to be on the lookout for is if the expression is a product quotient of factors, consider the reciprocal or quotient identities. If squared terms are present, we want to think about those Pythagorean identities. And if we have a negative argument, meaning the thing that we're applying the trig function to, in this case it would be x, if that's negative, we would want to think about the even or odd function identities. We want to keep in mind all the basic algebra techniques that we already know, such as factoring and multiplying and working with fractions. And another thing that can be very helpful is writing the expression in terms of sine and cosine, and then seeing kind of where you can go from there. So when we take a look at this one, that's the first thing that I really noticed, that I have tangent and cotangent, and I can write those each in terms of sine and cosine using those quotient identities. So that's what I'm going to do first. I'm going to say, okay, instead of tangent, I'm going to write sine x over cosine x. And instead of cotangent, I'm going to write cosine x over sine x. And so when I do that, now just thinking about multiplying these fractions together, right, the cosines cancel, The signs cancel, so all I'm left with is 1. Let's consider another one. Let's get ourselves some space here. Okay, so similarly, let's take that same strategy. I'm going to write cotangent in terms of sine and cosine. So instead of cotangent, I'm going to think of cotangent as cosine x over sine x. And cosine, again, we can't do anything with that, so we'll just leave it as cosine x. So now you need to think about how I would divide fractions, right? Cosine x as a fraction would be above 1. And then when I divide fractions, I keep the top, and then I multiply by the reciprocal of the bottom. So I flipped the bottom. So now when I multiply, again, remember I can cancel that common factor on the diagonal. So what's left is 1 over sine x. Remember, I'm writing this as a single number, like the previous question. That single answer was the number 1, or as a single trig function. So I know that 1 over sine x, thinking of the reciprocal identity, is the same as cosecant x. So that's my final answer. Okay, let's take a look at one more. This last one is a little bit more complicated, so let's kind of talk through some strategy here. Okay. So now I see those squared functions. So I want to think about the Pythagorean identities. So here we have 1 plus tangent squared x. So let's take a look again at those Pythagorean identities. So here's the one that has tangent. So tangent squared x plus 1 is equal to secant squared x. So that means I can replace 1 plus tangent squared x with secant squared x. Okay, so now from there, I can think, okay, I can rewrite secant in terms of cosine, right? So secant squared x is the same as 1 over cosine squared x times sine squared x. Remember, sometimes it's helpful to think of everything as a fraction so we don't confuse what's a numerator and what's a denominator. So now when I multiply across, I have sine squared x over cosine squared x. And I know that sine over cosine is tangent, and since it's squared, it would be tangent squared x. So one last thing to note about those Pythagorean identities is that they have different forms, right? These are written out each using sine, cosine, tangent, secant, and relating cotangent and cosecant. But you can solve these equations for any one of those functions, right? So for example, just as a quick aside, I'm just going to write right here. You know, so like that second one, tangent squared x, plus 1 equals secant squared x. So I could solve for tangent squared x, right? So tangent squared x is equal to, if I subtract the 1 to the other side, secant squared x minus 1. So that would mean anytime I see the expression secant squared x minus 1, I could replace it with tangent squared x. So keep that in mind when you go to manipulate these expressions using the Pythagorean identities.